Hello, welcome back. We have been discussing the applied physics. In this video, we'll discuss the Hall effect. The Hall effect was invented by Edwin Hilbert Hall, where a piece of metal or semiconductor which is carrying current is placed in a magnetic field that is perpendicular to the piece of the semiconductor or metal. Then, due to the presence of magnetic field, a force will be exerted on the charge carriers, and the charge carriers will be accumulated on either edges of the strip. Due to the presence of the magnetic field, the charge carriers will be deflected. Say the charge carriers are moving with a velocity v. Due to the Lorentz force, these charge carriers will be deflected. As a consequence, charge accumulation takes place on the edges. Thus, accumulated charge carriers will establish an electric field which will oppose the further accumulation of the charge carriers. At equilibrium, we'll find out a relationship which is called as the Hall coefficient. The definition goes this way. The Hall effect. When a piece of conductor, metal or semiconductor, carrying a current is placed in a transverse magnetic field, an electric field is produced inside the conductor in a direction normal to both the current and the magnetic field. This phenomenon is known as Hall effect, and the generated voltage is called the Hall voltage. Here, when a piece of conductor, metal or semiconductor, carrying a current is placed in a transversive magnetic field, an electric field is produced inside the conductor in a direction normal to both the current and the magnetic field. This phenomenon is known as the Hall effect, and the generated voltage is called the Hall voltage. Here you have a p-type semiconductor, and here you have an n-type semiconductor. You have the magnetic field here that is pointing downward, and you have a current passing through the strip. Here the semiconductor is taken in the form of a strip whose thickness is T and width is W and length is L. Now this semiconductor is placed in a magnetic field BZ pointing downward. As a consequence, a Lorentz force is acted upon the majority charge carriers or the holes in the case of a p-type semiconductor, and these charge carriers will be deflected to this edge of the semiconductor. Because the charge carriers are deflected to this edge, charge accumulation takes place on this edge. So thus accumulated charges, they establish an electric field given by E. The magnetic field in the negative direction along the z-axis, current is along the positive direction of the x-axis, the established electric field is along the y direction, the current and the magnetic field are perpendicular to one another. Similarly, in the case of an n-type semiconductor, the majority charge carriers are electrons, and these electrons will be deflected to this edge, because here we have reversed the magnetic field direction. So there will be accumulation of charges on the edge of the semiconductor on the sample, and because of these charges you will have an electric field in this direction. The electric field thus established is called as the Hall effect. Because of the established electric field, you will have a potential difference between these two edges, and the potential difference is called VH here. It can be observed using a sensitive galvanometer, and the voltage that we measure in this experiment is called as Hall voltage, and we have a current passing through the semiconductor. Now let B be the magnetic field that is applied. So the applied magnetic field is B, and the type of semiconductor we consider in the present situation is n-type semiconductor. Say V is the velocity of the electrons. The electrons will experience a force, that is the Lorentz force, Due to the presence of the magnetic field, the force is given by BeV, where E is the charge of the electrons. Due to this particular force, the electrons will be deflected and accumulated on the edge. Due to the accumulation of the charges on the edge, we'll have an electric field. The electric field is represented with a EH, representing that this electric field is established because of the Hall effect. At equilibrium, the force exerted on the electrons by the magnetic field or the deflecting force exerted by the magnetic field on the electrons will be equal to the force exerted by the Hall field or EH on the electrons. So we write EH is equal to BeV. Say this is 1. We write EH is equal to BV, and we know that current density J is equal to NeV, where N is the electron density in N-type semiconductor. E is the charge on the electrons, V is the velocity. Then we write from this velocity V is equal to J by Ne, and we'll substitute this in 1. We get EH is equal to Bj upon Ne. We'll call this 2, and we'll introduce a quantity that is called as Hall coefficient, represented with RH, which is defined as RH is equal to 1 over Ne. So we write EH is equal to RH Bj, or RH is equal to EH upon Bj, that is equal to 1 over Ne. Since in this expression RH is equal to EH upon Bj, which is equal to 1 over Ne, EH, B and J, they can be measured. Since these three quantities can be measured, one can measure the density of electrons in the N-type semiconductor. Since the electric field is established in the opposite direction to that of the accumulation of the charges, we write RH in this case as minus EH upon Bj, or this is equal to minus 1 over Ne. And similarly for a p-type semiconductor, one can write RH is equal to EH upon Bj, which is equal to 1 over Pe, where Pe is the density of holes in the p-type semiconductor. Now we shall see the applications of the Hall effect. Using the Hall effect, one can determine the determination of type of semiconductor, depending whether the Hall coefficient RH is positive or negative. If RH is positive, then it is a p-type semiconductor. If RH is negative, then it is an N-type semiconductor. The second application is calculation of carrier concentration. Since we know RH is equal to 1 over Ne, in this we can determine RH. E is, that is the charge of the electrons, is known to us. We can find out N, that is equal to 1 over ERH in the case of an N-type semiconductor, and P is equal to 1 over ERH in case of a p-type semiconductor. The next application is determination of mobility of the charge carriers. We know that conductivity sigma n is equal to Ne mu E, where sigma n is conductivity of electrons in the N-type semiconductor and mu E is the mobility of the electrons. This implies mu E is equal to sigma n upon Ne, or that will be minus sigma n RH in the case of N-type semiconductor, and mu P, that is the mobility of the holes, which is sigma P RH. This is applicable in the case of p-type semiconductors. Further, this can also be used to measure the magnetic flux density. So, measurement of magnetic flux density. We know RH is equal to VHT upon IB, where T is thickness of the sample, I is the current through the semiconductor. Then we write B as VH, that is the Hall voltage, times thickness of the semiconductor upon current through the conductor times RH, that is the Hall coefficient. This is how one can find out magnetic flux density using the Hall coefficient. In this video, we have said what Hall effect is. When a piece of conductor, for that matter metal or semiconductor, carrying a current is placed in a transversive magnetic field, an electric field is produced inside the conductor in a direction normal to both the current and the magnetic field. This phenomenon is known as Hall effect, and the generated voltage is called the Hall voltage. We have seen the simple experimental setup in the case of a p-type semiconductor and n-type semiconductor. T is the thickness of the sample, W is the width of the sample, L is the length of the sample, Bz is the flux density, and Vh is the potential difference measured across the width of the sample, and I is the current through the semiconductor. In the case of p-type semiconductor, the current is mainly due to the holes, and in the case of n-type semiconductors, the current is mainly due to the electrons. We have written an expression for the Lorentz force acting on the electrons as BeV, and the force that is exerted on the electrons due to the Hall effect. The force is E, capital EH, where EH is the established electric field due to the Hall effect, that is equal to BeV. We have obtained EH is equal to BV, and from there we have obtained EH is equal to BJ by NE, where J is the current density given by NEV. We have defined a quantity called as Hall coefficient RH. RH we have defined as RH is equal to 1 over Ne, where N is the carrier concentration of the electrons and E is the charge of the electron. So RH we have written as EH upon Bj, which is equal to 1 over Ne. In the case of electrons, the electric field is established opposite to the direction of the deflection. So we have written Hall coefficient as minus 1 over Ne. And in the case of p-type semiconductors, we have written the Hall coefficient as 1 over Pe, where P is the density of holes in the piece of semiconductor. We have discussed the applications of the Hall effect. Hall effect can be used to determine the type of the semiconductor. Using the Hall coefficient, one can say whether the given sample is a p-type semiconductor or an n-type semiconductor. One can calculate the carrier concentration of the given semiconductor. One can determine the mobility of the charge carriers in the given semiconductor. One can also measure the magnetic flux density using the Hall effect. Thank you.